That's 1, 2, 3, 4, 5, 6, 7, 8. Test, test. Hey, just take one papers there. Yeah, so little time. Take the papers, the exercise papers there. Let's take one papers here. Hey, take the papers here.
Will you do a lecture now, or?
I will explain the exercise first, and after that, they will try. Then we can just guide
Okay,
them.
yeah, because I haven't seen the exercise. You did.
Huh?
You didn't send it to me.
No, I send it to you.
No, oh, I thought it was a.
The second page.
Wasn't it just a? Okay, yeah, sorry. Sorry. I thought it was a lecture or something,
Oh.
but I looked through it.
No, that's just the exercise. How to build.
Yeah, so just like top that down lab.
Yes, and
Yeah.
after that to make Chronostratigraphy and ecstasy.
Yeah.
Uh-huh.
All right.
take the exercise paper there.
I'm just gonna go and get some
Yeah,
water.
no problem. Is anyone still upstairs? Three. Okay. Regarding the Petrel software, I think I said on the email that you can install Petrel software in your laptop, your own laptop, and then you can work everywhere in the world as long as you connect to the internet. So once you have a Petrel in your laptop installed, then you can access the license, the NTNU license, using VPN. And then it means that you need to use your NTNU account. So, and after that, you can work everywhere in the world as long as you have internet connection. But maybe since the segue file is like 2 or 4 gigabyte, so if your laptop memory is low, then when you turn when you visualize the 3D, it's gonna be like tuk, 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 tuk. But if it is just to make some horizons and fold, it will be fast. So you do, yeah. It's heavier than MATLAB. So it means that you don't need to work in this lab all the time. So you have it in, it's on the, no, it's on my lecture slides. Hey, take the exercises paper. That one. But I will send this soft copy of this to Blackboard. No worries. I think all of you are here. So if you remember our last Tuesday lecture is about seismic sequence stratigraphy, and I promise you to give exercise about this seismic sequence stratigraphy. It's basically to build seismic facies analysis, make a chronostratigraphy, and then make a eustacy of sea level from this seismic section. Okay. So today we will discuss about this, and I have put some reference in the Blackboard regarding this exercise. It's mostly from this book, APG Memoir 26. It's about seismic stratigraphy. So for this exercise, we will use mostly in the part 3, seismic stratigraphy and global changes of sea level, relative changes of sea level from coastal onlap. So we will utilize coastal onlap mostly to define the eustacy of sea level. But we also need to define another reflection termination pattern on the seismic facies analysis. So the first step, what we need to do is, of course, we need to interpret this section. So I will try to interpret this section. The X number is the age in million years, starting from the oldest one, X25, to X1 in the upper part. And this is zero phase seismic, and then is it, and done? Oh, okay, you can take this one. That's a zero phase seismic, and then you have the information of scale, horizontal and vertical scale. Can I borrow? I'll give it to you. So first, what you need to do is to interpret the seismic section. Basically, it's a stratigraphic interpretation. Yeah. That's the first one. So I will take the major reflector here. So this is X25. And I'll take the X17. So this is X17. And I'll take the X12, 13, 14. X14, yeah. And I'll take 6, 5, 4, and I'll take this X4 and X1. Okay. X4. X3, X4. Oh yeah, right. X3. Yeah, X3. So in the this one is exactly the same with the Petrel models when we discuss system tracks. Okay. So in this X25, what we have is we have this downlap and we have this onlap. Okay. And it's the same with X24, 23, 20, 22, 21. We have onlap to this site. This is a proximal set. And this is distal. Okay. And remember, this is all is a marine sequence. Yeah. So it means that this is a shallow marine, and more to this place is the deep marine. Okay, and then if you look at this X17, so the X17 here is the line where the reflector below is truncated in this area. Did you see? So the reflector below X17, especially X18, X19, are truncated in this area. Okay, so it's truncated. And reflector reflector above X17 in this area, it's downlap to X17 like this. And its onlap reflector above X17 in this area is onlap to this reflector. So it means that this X17 is, what kind of boundary is this? This X17. You have a truncation. In this case, erosional truncation. Even you can see some incision here. Can you see the incision? Here, you have some incision in this area when you are truncated. So it means that you have a valley in this part. So it means that this X17 is sequence boundary. Okay. And then if we define the system tract from this section, this is exactly the same as the system tract that we discussed last Tuesday. So in this interval here, we have a gradation, but also so mostly a gradation, and then we have a downlap here and onlap here. So what kind of system tract here in the first sequence here? We have a gradation, mostly a gradation, and we also have a sequence boundary at the top of this sequence. So what kind of system tract do we have here? High stand system tract, yeah. This is high stand system tract. And above this sequence, okay, just say A is high stand and B is prograding, mostly prograding, and at the end we have some retrograding, little bit retrograding, but mostly prograding. Submarine fan. So we have what? Low sensitive tract, yes. And this one, this interval here, we have backstepping. If you look at this from X3 to X3 to X12, you have a mostly backstepping to this proximal part. Means you are in the transgressive sea level. So you have what kind of system tract? Okay. So this is transgressive system tract. Okay. So we have A, B, and C, just these three first. And next, thank you. So based on this procedure to make chronostratigraphy and use to see, the first step is to analyze the maritime sequence. Just put A to E in this sequence. These steps include the determination of sequence boundaries. We have sequence boundaries, age, areal distribution, and the presence of coastal onlap and top lap. So we have defined downlap, onlap, and is this the same for this sequence? Even we have this truncation here. We also have this downlap in this sequence, and we have this top lap here. We have this downlap here and onlap here. Okay. And for the maritime sequence, so as state on the figure, this is all is marine, but what we need to define is the boundary. So we know that this is a coastal, but the boundary of self-edge position is defined in this point. So if you look at this sequence, you have a kind of plunging like this, and this point, that is the self-edge, it means that this one is more shallow and this one is deeper. Okay, so you're just pointing the self-edge position. That can give you understand that this one is this area here is shallow and this one is deeper. Like for instance here, so if this is the self-edge, means this area here is shallow and this one is deeper. Okay. This one, self-edge point, or rollover point. Yeah, it's the same. It's the same. Yeah. Okay. The second step is to construct a chronostratigraphic correlation chart of the sequence. This chart, remember when we discussed about the seismic reflector following geological timelines. Do you remember this plot? So if we have something like this is distance, and this is depth today. So this is a seismic section. And then this is chronostratigraphy. What you have here is distance and relative geological time. So for instance, if this is time 1, time 2, time 3, so you have 0, 1, 2, 3. What you have for time 1 is this one. What you have for time 2 is this one. What you have for time 3 is this one. Remember this one? So basically, we want to reconstruct all this reflector into following the geological timeline. Okay, so what you need to do, just the second one here is chronostratigraphy. So what you need to do, just take this point here and the last one here, like this. And this axis will be the geological timeline, relative geological timeline. So this one is relative geological timeline. It means that this one, 25 until 3. This is millions years ago, yeah, X. So if we put this, for instance, 25, and I put this 17, and then 14, and then 3. So now what you need to do, just to plot this to this to make this flat. So just interpolate like this. Okay. And then from here, from this point to this point, that's the reflector of X25. Okay. And the same for the rest. Then I will do the 17. So 17 is here and here. So this is X17 and 14 start from here and downlap here. 14, yeah, and this is 14. And x3 start from here and stop here, so it's all the way to the left like this. Any question? Good. Okay, what's next? So if you look at this area here, this place here, for this x25, it means that if you remove all this sequence, so just only x25, it means that at the time of x25, like this, so this is x25, so you have this rollover points or self-edge points, self-edge points or rollover points. It means that your sea level is here, okay? And then remember we are dealing with this coastal onlap, so this is coastal onlap. And it means that this area here, that's the land, where we have the land. It means that there is no deposition in this area, right? So no deposition in this area at the time of x25 deposit, okay? It means that if there is no deposition here, it means that this area here is what we call as hiatus. So you can imagine from one seismic section that you have, you can make something like this. Okay, so now the third step is to create relative sea level. So number 3 is relative sea level. Okay. Yeah. Place. Okay. So the third step is to identify the cycles of relative rise and fall of sea level. And the key points in this relative sea level are coastal aggradation is the best measure of a relative rise, and downward shift of coastal onlap is the best measure of relative fall. So coastal aggradation means a relative rise. So coastal aggradation means relative sea level rise. Why I called relative? Because there is no exact number on this sea level, so that's why we call it as relative. And downward shift of coastal onlap is the best measure of relative fall, sea level. Downward downward shift of coastal onlap. Downward shift of coastal onlap is relative sea level fall. And coastal top lap indicate relative still stand. So rise, fall, still stand from these key points: coastal aggradation, downward shift of coastal onlap, and coastal top lap. Okay, so that's why the seismic facies analysis, seismic reflection termination, seismic reflection configuration is important in this stage. Okay, so you need to understand the reflection termination, like top lap, on lap, down lap, off lap, everything, and then seismic reflection configuration, and relate all those seismic facies to the interpretation of geology. In this case, the sea level. Okay, on the relative sea level, what you need to do is to plot this. So again, this one is the same. In this axis is relative geological time. We just make the same as this one. 25, 17, 14, 3. And after that, this X25 is the first position of the sea level. So we just put this like this, X25, and mark this as the first self-age position. Yeah. And after that, from this X25, this one, to X17 is this one, we need to measure the distance. Let me see. Okay, so so then what we need to do is that, so remember, we are using this coastal position. So we have, in this case, this is the coastal onlap position. So from this coastal onlap, then we need to measure the thickness of this coastal onlap to the next sequence. In this case is X17. And if you look at your section, you have this vertical axis in meters. So just measure this x, and then in this axis, this is the axis of meters. So this is 0, this point, the first self-edge. So this is, and this way is positive, means sea level rise. And to these directions is negative, means sea level fall. Okay. So can you measure how much how many meters from this point to the X17? Sorry? 500? 500? 500? Can I see? Yeah, more or less. Yeah. So it's 2 centimeters. Yeah, more or less. Yeah. So then we can say that this one is so if this is 0, this is 100, and this is 500. So it means that from this point to the second the second sequence is 500 meters, and you see this sequence, what you have is coastal aggradation, because if you look at your sections, the reflector is going like this, so it means you have a aggradation, right? So it means that you are in the relative rising sea level. So then the 500 should be goes to the right, not to the left. Okay. So then just take this point to X17, 500 meters here. So this is 500 meters. Just take that point, 500 meters. Okay. But later when you try at home, just use it every one reflectors. Because in every one reflectors, there's a age. This one just to make it simplified. I just take the big size, the big sequence, like this A, B, and C. But later, you need to do it every single reflectors. And then this 500 this 500 will be like a stair steps then. You see? So this 500 in my interpretation is just one straight line, because I only take this one and this one. But when you take every single reflector, it means that the relative sea level will be stair steps in this case, right? Okay. So next, from this point, now you see, now this is the good case. So from this point, the next sequence is this B, okay? What happened here? This point is moving to these directions. Means that you have downward shift on coastal onlap, because now if this is coastal onlap, but now the coastal onlap is moving to these directions, it means that it's the downward, okay? So downward shift in coastal onlap represent the relative sea level fall. So now we need to go to that directions, okay? So now if we need to move this point to this direction here. So this is the self edge. So we just put this point here to be able to calculate how many meters the sea level need to fall. Okay. So now, can you measure how many meters from this X14 to X17? How many meters? From X14 to X17. So from X14 to this. So this from the self edge of X14 to the X17 vertical. How many meters? Less than 100. So 90 meters, for instance. So then just put this. So it means that from this point, we need to move 90 meters from this point to that direction. So it means that the next X14 is here. So maybe, so 500 minus 90. So it's somewhere here. So then it's moving like this. Okay. So from this point, this is minus 90 meters. And the last one is this TST. So in this TST, what you have is, again, you have this aggradation like this, right? So it means that in this package, you are rising your sea level because you have this coastal aggradation, okay? And then you just measure the distance from this point vertically. How many meters? From X14, just take all the way up to X3, 500, 6. So from here, then to this, and then we need to go to the right because this, sorry, this is to the right. So this is to the left. It means rising. From here to this one, it should be out of scale here, like this. So this one is 600 meter plus, means rising sea level 600 meters from this point. Okay. So now you can try into more detailed interpretation. Then me and Oda is here, so we can hang around with you guys if you have any question. One more thing, you can also relate the system tracks in this sea level curve, since you have defined the system track there. So it means that this area here is where you have this high stand, and area here where you have this low stand, and this area here where you have the transgressive system track.